So more rules for calculations. If you're doing an addition subtraction, you have to put the decimal place, and then you have to actually you really have to line up the numbers. So here's some numbers. So what you do is you draw the line by the decimal place with the fewest number of significant figures. So this thing only is significant to the hundredths. It doesn't have any numbers here, so this is not significant. So when you do the addition, you get this. This is what your calculator spits out, but you're not going to count these as significant because these are after this insignificant number. There's no numbers here, so according to my column, these are not significant numbers. So my final answer only has these 3 significant figures. But so in this case, we're not actually counting number of significant figures. So the number of significant figures here is only 1, but we're not ending up with 1 significant figure. We're going by the column. Okay, so here's my subtraction, and I draw my column by, there's no number here, so I'm going to draw the column like this. So once again, we're not counting number of significant figures, we're going by the column. So when I do my math, I come up with this. This is what your calculator spits out, but you're only going to have this as your significant figure because this is what your column says is where the significant figure ends. So when you're doing addition, subtraction, unlike multiplication, division, where you actually count the number of significant figures, in addition, subtraction, you want to draw a line by the number with the fewest decimal point. So then that line determines your significant figures. So rules for calculations, rules for rounding. So when you're rounding, you have to have the correct number of significant figures. So you have to round down if the last digit is less than 4, or less than 5, so it's 5 or less. You round up if the last digit is 5 or more. You know, this is just the standard rounding up rules that everybody uses, you know, since the beginning of, so you should know. So rules for rounding. So here we have these bunch of numbers, and we want to round to 2 significant figures. So that last bunch of numbers are not significant. So here you got 5.37, so we have to round it up to 5.4 because the 7 is greater than 5. So you got 5.34. That last number is 4, which is less than 5, so you round it down to 5.3. Okay, so now we got this, which is 5.35. So that last number is actually a 5. So it's 5 or greater, so we're going to round up to 5.4. Now here we've got an extra number down here. So let's say we have 2 significant figures, and this is what your calculator spat out. So you might think to yourself, oh, well, maybe I should round this up, so then this becomes 5.35. And then when I round that up, then it becomes 5.4. But that's not what you do. You don't look at this number at all. All you do is you look at the very last number, so then it only goes to 5.3 when you round up the number. So in the last example, so this example here, only the last or leftmost digit that's being dropped determines rounding. So it's only the 4 that determines the rounding. We're not going to look at the 9 and the 4. We're only going to look at the 4. So you ignore this number. So when you're doing multi-step calculations, so you do a bunch of calculations before you come up with the final answer. So how do you round that? So in order to avoid rounding errors, what you want to do is don't actually round in the intermediate steps, because if you do, it can actually significantly affect your results. So you just keep writing down all the numbers for all your intermediate calculations, and then at the last minute you do the final rounding up. So this thing has 3 significant figures, this thing has 4 significant figures, this thing has 4 significant figures, this has 3 significant figures. This is an addition subtraction, so you'd have to put them in a column. and then this is a multiplication division, so you'd actually have to actually count the number of significant figures. So when you're trying to come up with the number of significant figures here, you'd actually have to write up the column, and you would note that the significant figures here is actually right where the underlined number is. But you're not going to round it up at this point. You're going to go ahead and use that number. You're going to go ahead and stick it into your calculator, come up with the final answer, but you're not going to use all of these digits that your calculator spat out as your final answer, because this is the significant figure because of the columns when you do the subtraction addition. So then this number only has 2 significant figures, even though I wrote down 3. I wrote down 3 because if I leave the last number out, it may affect your calculation results. So you go ahead and keep it in writing, but you remind yourself where the last significant digit is by underlining it. And then you stick it into your calculator, and then you note that this only has 2 significant figures, so your final answer should only have 2 significant figures. So this is your final correct calculated number with the correct number of significant figures. So what is precision and what is accuracy? Accuracy is how close the measurement is to the actual correct number. Precision is how close, when you're doing a bunch of measurements, if all of your numbers are all coming out very close to each other, that is precision. You don't really know whether the precise numbers are actually the actual numbers, but you do know that the numbers are coming out very close to each other. Okay, so more stuff about precision and accuracy. So if you have if you're looking at the results of 3 students, so this is a specific example with numbers. So let's say you have 3 students, and they are asked to measure the weight of a block, and it's known to weigh 10 grams exactly. So what happens when you have the 3 students do their work? So student A gets an average of 10.13, which is not 10.00. Student B gets an average of 9.79, which is also not 10.00. Student C gets 10.01, which is very close to 10.00. So of these 3 students, student C has an accurate result. Now let's look at precision. So let's look at what's going on here. 10, 9, 9, 10. Ooh, this guy's got number all over the place. What about this guy? This guy has numbers that are very close to each other, so this is a fairly precise set of numbers. These are very imprecise. So let's look at the chart for the precision and accuracy from the last set of measurements. So precise is if they're consistent, accurate if they're actually close to the actual correct number. So here, this blue line is the actual true mass. So it should weigh 10 grams. So here's the true number. Okay, so this is inaccurate and imprecise. It's inaccurate because the average comes out up here, and the average comes out here in the red, the pink dotted line, and here's your true value. It's imprecise because you got like numbers all over the place. It's like throwing darts, and the darts are showing up all over the board, and it's not, none of the numbers, that the average is not close to the actual number. So this is both inaccurate and imprecise. Okay, so this one is inaccurate and precise. Why is it inaccurate but precise? Because here's the actual number, here's the pink number. It doesn't exactly match up, so it's inaccurate. It does not actually average out to be the correct number. However, this guy had all of his measurements fairly close to each other, so they are precise numbers. They're just inaccurate because they're very far away from the actual correct number. This last student, student C, has numbers that are both accurate and precise. Why is that? Because his pink line is right at, the average line is right at the blue line, the accurate, the actual correct number. The other thing is all of his numbers are very close to each other, so they're fairly similar to each other, so they are also precise. So student C has numbers that are both accurate and precise. So when you're solving chemical problems, you'll see that you have a lot of unit conversion problems. So there is a way that you solve all of these, and this is by using something called dimensional analysis. And what you'll find is that you can solve maybe 90% of the problems that you get in chemistry classes, in general chemistry classes, using dimensional analysis. It's that powerful a thing. So when we go over the initial stuff that where you just go from grams to using density, from going from grams to liters or something like that, that's just a one-step problem. But if you do dimensional analysis on a whole bunch of things, you can go from something like liters of water to number of atoms of hydrogens in that liter of water that you have. So dimensional analysis is a very powerful thing. And what you do is you can, and the thing that you want to remember is that the unit of measurement, so this is 1.25 meters, the unit being the meters. Whenever you do, whatever you do to the number in your calculations, you multiply, you divide, you square, whatever you do to the number, you also have to do to the unit. So as long as you keep the units together with the number and do the same thing to it, you always get the correct answer. So what you do in dimensional analysis is you multiply by 1 until you get the desired unit. So what do I mean by multiply by 1? You don't really multiply by 1 multiple times. It's not really 1. But what you do is you write out a unit equation. So here's a unit equation. We know that 2.54 centimeters is equal to 1 inch. So this is equivalent to that. So this is a unit equation. So that this number is the same as that number. So when you write out a conversion factor, what you do is you write out this unit equation as a fraction. So you either say 2.54 centimeters over an inch, or you say 1 inch over 2.54 centimeters. And you use that to convert from where you're starting to where you want to end up with. So what you do is you use the equation where where you're converting from on the bottom and where you want to end up with on the top. So in dimensional analysis, you multiply by 1 until you get the desired unit. And most unit conversions are sort of like this. So you got some information given. So somebody tells you, you've got 2.54, sorry, not 2.54. Let's not use that number, because that looks like the number that we are using for our unit conversion factor. Let's say somebody tells you you've got 400.2 grams of something, and they want you to come up with the number of kilograms of that thing. So the information given would be the 400 grams. And then you're going to have a conversion factor, and then you want to get the information that you're looking for. So you look at the number, but you also look at the unit of that measure. So if I gave you 400.0 grams, you would look at the gram. And then you multiply by this, where the bottom is the unit of measurement that you're given, so grams and grams. And then you want to look at the desired unit. So the desired unit, let's say, was kilograms. So then you want to end up with the final desired unit. So this is the way that most of these dimensional analysis problems are done. If you have a unit of measure, so feet, meters, centimeters, whatever, if you have to raise something to a power, whatever you do to the number, you also do to the unit. So here's an example of that. So let's say we have 2.54 centimeters equal to 1 inch. And let's say our unit is, we actually have to have centimeters squared. So if you do centimeters squared, what you do is you actually do the entire number and the unit. You treat it the same. So whatever you do to the number, you also do to the unit. And you square the entire thing. So you square 2.54 centimeters, and you square 1 inch by you do whatever you do to the number, you also do to the unit. So if you are squaring it, then you square the number and you also square the unit. You square the number and you square the unit. So if you square the number, stick it into your calculator, 2.54, and then you square that number, you get 6.45. And the unit of that 6.45 is actually centimeters squared, because whatever you do to the number, you also do to the unit. So here, when you take 1 and square it, you still get 1, but you also had to square the inch, so now it is inch squared. So this is 6.45 centimeters squared and 1 inch. So if you actually had this, because 2.54 centimeters is equal to 1 inch, 6.45 centimeters squared over 1 inch is also equal to 1, because if you had 2.54 centimeters over 1 inch, it would also be equal to 1. So that's what you do if you have units that are raised to powers.